The UK Engineering and Physical Sciences Research Council has recently funded a consortium of 6 universities to work on different aspects of solar power. And the reason we need this research is because traditional solar cells are made from crystalline silicon, which, although the price has dropped recently, it costs a lot of energy to make. There are efficient alternatives to silicon, such as cadmium telluride and other materials, but these materials are scarce. If the world is going to increase its use of solar energy, then we need to find more easily sourced alternatives. At the University of Bath, we are looking for such sustainable materials. And we are also looking at novel types of solar cells which can be made to be flexible and very light, unlike conventional silicon, which has to be encased in glass and is therefore fragile. These new solar cells will work in diffuse light, which is, after all, the conditions in which we traditionally find ourselves in this country.
My group is working on the development of new materials for solar cells. We perform computer simulations on the fundamental building blocks of matter: atoms, ions and electrons. So we combine high-performance computing resources, so some of the largest supercomputers in the world, with basic tools of quantum chemistry, which have been developed over the last century. So the ultimate aim is to predict the properties and performance of materials even before they've been made in the lab. As part of the Super Solar Hub, we're working at overcoming the limitations of the current generation of silicon-based solar cells. So we're looking at new materials that can have similar performance in terms of converting sunlight to electricity, but at a lower cost and that are more scalable. So one recent success is kesterite, a new material formed from just copper, zinc, tin and sulfur, which are all quite low cost and abundant elements. So these are very important factors if we're looking at scaling up solar cell technologies to meet a significant fraction of our energy needs. So why kesterite materials are generating a lot of excitement is because they absorb light very strongly. So for a silicon-based solar cell, we need a relatively thick film, for example, the thickness of this book. For a kesterite-based device, we can get away with using just a couple of pages. So the amount of material used is diminished and the cost of the overall device is lower, while keeping similar performance. So once we have a robust theoretical understanding of how material works, how it interacts with light, and how we can optimize its performance, then we pass this information on to our experimental collaborators to actually synthesize the materials.
So traditional solar cells are often made using expensive high vacuum techniques, or the materials for the solar cells are solution processed from harmful organic solvents. This can make quite high efficiency solar cells, but there's obviously an environmental impact associated with that. One of the things we're doing in my research is looking at trying to prepare materials that are processed from water as an environmentally friendly solvent. In my lab, we make different materials and we put them into test cells. So we typically make 1 centimetre squared test solar cells and measure how efficient they are and how they behave. The next step in the research is normally to do some whole device modelling to try and understand better how all the different materials in the solar cell interact with each other.
So my work is to understand the currents that come out of real cells, such as this one. And what I do is I take Aaron's work, which shows how the free charges are generated when light is absorbed. I follow the trajectories of these charges as they flow through the device, and I can then predict currents, which is what Petra measures. So I can compare my predictions of the currents with Petra's measurements, and we can use the comparison to update our knowledge of how these cells work, and more importantly, how they stop working, because these cells degrade quite quickly and we want to find designs that give them a longer lifetime. I've recently got European funding for a network called Destiny, which is training graduate students to understand these degradation processes. The impact of this work is to create jobs in the UK, because there are already spin-off firms that exploit it, but there could be many more jobs if the technology can be got working. But to get it working, we have to get the science right, which underpins these different technologies. But most importantly, we want to make solar power a more viable technology worldwide, and thereby encourage the use of renewable energy and mitigate against the effects of climate change.